Good morning, all. Respected teachers of the department, our chief guest, Professor Govind Krishnaswami from CMI, and dear students, we have gathered here for the 6th annual memorial lecture in homage to Professor MC Valsakumar. I would like to introduce, say a few words about Professor Valsakumar to the students. Some of you might have been here for the previous 5th lecture last year. Professor Valsakumar, he hails from Talassery in Kerala. He completed his degree in Government Brennan College and then PG in Calicut University Physics Department. After that, he joined Department of Atomic Energy through BARC Training School. So he was a senior scientist at IGCAR. He spent there some 32 years, some long period there. He retired as an outstanding scientist from IGCAR. And during his stint at IGCAR, he was famous throughout India as a person with strong theoretical physics research contributions. He worked in open quantum systems, statistical mechanics, and many condensed matter theory and many areas of theoretical physics. He was also involved in installing a high computational facility at IGCAR. And towards the end of his career, he worked in computational material science also. After his retirement, he worked in HCU for 2 years as visiting professor. And then IIT Palakkad, when IIT Palakkad started, at that time he was a visiting professor there. And Professor Valsakumar was an honorary member of our organization, Academy of Physics Teachers. And this is a professional organization of physics teachers of colleges and universities in Kerala. So Valsakumar's sudden demise in 2019 January was considered as an immense loss for the teaching community in India, physics community in India. So some of his students, friends and colleagues set up an endowment fund, both at IIT Palakkad and with APT, Academy of Physics Teachers. In IIT Palakkad, I think every year, in May, there is a 10-year residential program going on for 11th standard students to bring them to basic physics, basic science. And in Academy of Physics Teachers, we conduct this annual memorial lecture. This is every year we do it in theoretical physics, a particular area in theoretical physics, to bring the students to the research opportunities available in theoretical physics area, to make them familiar with the different theoretical physics areas. So this is our 6th lecture. And today our speaker is from Chennai Mathematical Institute, Professor Govind Krishnaswami. On behalf of Academy of Physics Teachers and on behalf of Department of Physics, Cochin University, this is of course a joint venture of both Academy of Physics Teachers and CUSAR Department. So on behalf of all of us gathered here, I welcome Professor Govind Krishnaswamy to this program. Welcome, sir. And the President of Academy of Physics Teachers, Professor Sindhu Jones is here. She is Principal of Catholic Aid College at Pathanamthitta. On behalf of all of us, I welcome Madam. And the family, the Mrs. of Valsakumar sir is here. Srimati Leela, Madam is here. And his family is here. Welcome, Madam. And his friends and colleagues are here. From PRL Subramanian sir, he was a colleague and friend of Valsakumar sir, and Matthew sir, who was a colleague at IIT Palakkad. Professor K.L. Sebastian sir, he was also a colleague of Valsakumar sir at IIT Palakkad. Incidentally, you might have read in today's newspaper that Professor K.L. Sebastian sir has received state government's Kairali Lifetime Achievement Award for Research. Congratulations, sir, on behalf of all of us. And Professor Jairaj sir was we know that he was Vice Chancellor of Calicut University. And for Academy of Physics Teachers, more intimately, he was the President of Academy of Physics Teachers for 4 years consecutively. Welcome, sir, to this program. And all the colleagues, Shaji sir, and all other friends here, all colleagues here in the department, and all the students gathered here, I welcome all of you to this program. Thank you. And I welcome Sindhu Madam for presiding over this function.
Thank you, Hare Krishna sir. A warm good morning to one and all. Respected Chief Speaker of the day, Govind sir. Madam Jairaj sir. Dear teachers and dear students. Very happy to stand before you on this occasion as a president of APT for the 6th memorial talk of Valsakumar sir. Talking about him, I have been to his classes. I think I remember each and every thing he used to write on the board and very patiently discuss of any doubts if we would ask. So I think the last class which I attended was in CMS College. And I think the topic he took was the perturbation theory in quantum mechanics. The honor we give to Valsakumar sir is by taking lectures because he enjoyed teaching. When you look into his career, you can see that he had been enjoying teaching in different institutes. And today, we fondly remember him through this lecture on three-body. And we have with us the eminent speaker, Govind sir. And I think the starting itself, he has made a familiar thing within us, the sun, moon, and earth. So that is how a speaker should be, I think, because we have to start with what we are familiar with and then grow up in the lectures. So we are really thankful to you for coming over to this seminar and presenting your topic for our students too. And it is a great pleasure to invite Govind sir to this to our midst. And thank you each and all for being with us. Thank you very much. Best wishes.
A warm good morning to one and all. I am here to introduce Prof. Govind Krishnaswami. Govind Krishnaswami is a physicist in Chennai Mathematical Institute. After his schooling in Chennai, he went to the United States for his higher studies. He did his PhD with S.G. Rajiv under University of Rochester. And he's also the nephew of Professor M. Mukunda. He held his postdoctoral fellowships at Utrecht in Netherlands, UK, and also in Durham in UK before joining Chennai Mathematical Institute. His research spans various topics in quantum field theory, mathematical physics, nonlinear and fluid dynamics. He has mentored several masters and PhD students and has also lectured at various theoretical physics schools and workshops. And he has also taken classes for APT. He's a recipient of the Apker Award of the American Physical Society and the author of the book on classical mechanics. And with immense pleasure, on behalf of Department of Physics, CUSAT and Academy of Physics teachers, I invite Dr. Govind Krishnaswami to deliver the 6th Valsakumar Memorial Lecture on three body problems and invitation to dynamics and chaos. Thank you.
Okay, so is it? Yeah. Okay, so am I audible? Okay. Okay. So thank you so much for this kind invitation. It's a pleasure and an honor um, to contribute to this lecture series in memory and to pay homage to Professor Valsakumar. I thank the Academy of Physics Teachers Kerala as well as QSAT for honoring me in this way and for the very kind introduction. Yeah, so and it's nice to join the illustrious group of speakers you have had in past years. I did not know Professor Valsakumar personally. However, I did have the pleasure of meeting him at least once or twice. The last time I remember was at a workshop in southern Karnataka. It's in Alvas College in Moodbidri. So we were both lecturing over there, and I have only vague recollections of that. It was in 2016, and he was talking about non-classical aspects of quantum mechanics, yeah, entanglement and Bell's theorem and so on, I think. Yeah, so and I it's possible that somebody here was there as well. That was in 2016, and prior to that, I might even have met him at IGCAR in Kalpakkam, because I am from CMI, Chennai Mathematical Institute, and our students used to do summer lab work at IGCAR. So in that connection, I had been there, and we probably met in that connection as well. So it's a pleasure to be part of this program. I think the APT is doing a great job. And QSAT is a great host as well. Yeah, so I was just looking up. So it turns out that Professor Valsakumar is from the town of Pinrai, I believe, and that he studied in Government Brennan College in Thalassery. I was fortunate enough to visit both of these places a year ago. So I had been to Brennan College for some lectures, and after those lectures, one of the faculty was kind enough to take me on a ride to Perlassery, and in order to go there, we went through Pinrai. So I've been to at least the place he came from. Yeah. So okay. So with that, yeah, and I have had the pleasure of being part of the APT lecture workshops once before in Irinyalakuda. I think we had a weekend on scattering theory. Okay, so let me go on to today's topic. So I'm going to tell you about three-body problems and viewed as an invitation to dynamics and chaos. Yeah. Yeah, and this is based on work with PhD students, Himalaya Senapati and Ankit Yadav. This was done at Chennai Mathematical Institute. And let me tell you about it. So this is an abstract. And maybe it's good to read an abstract. So three-body problems, such as Sun, Moon, Earth, have been a rich source of ideas. Newton and Clairaut showed that it explains the precession of the lunar perigee. I will talk about these things. Euler and Lagrange found remarkable periodic solutions, while Poincare discovered chaos in this problem. Its study has shed light on the nature of singularities and catalyzed the development of techniques such as perturbation theory, canonical transformations, other things, resonances. Quantum versions are relevant to the helium atom and the hydrogen molecular ion. So after surveying some results and background, we will then turn to a more recent variant, which we call the three-rotor problem, where particles move on a circle subject to pairwise attractive cosine potentials. This problem is of independent interest as the quantum three-rotor problem models chains of coupled Josephson junctions. And these can be used to build a qubit. We show that the system displays remarkable dynamical phenomena, what are called choreographies, families of periodic orbits with accumulating stability transitions, isochronous and period doubling bifurcations, order chaos, order behavior, ergodicity in a band of global chaos, and both universal and system-specific manifestations of quantum chaos. So I might not be able to describe all of this, but I would like, if you have questions during the talk, please do ask. You don't have to wait till the end. That would be great. So this talk is based on a few papers. An introductory account of the three-body problem with references to the literature is available in Resonance. So Resonance is, of course, published by the Indian Academy of Sciences, and I recommend the journal to students as well as others. So we have a paper in that on introduction to the three-body problem. Okay, so let's come to the three-body problem. So this is the classical gravitational three-body problem. So in this, we approximate the celestial bodies like Sun, Moon, and Earth by point particles. So we have these point masses moving subject to their mutual gravitational attraction. And the equations of motion are basically those of Newton. Mass times acceleration is equal to the gravitational force. And now you have gravitational force from the two other bodies. So I labels the three bodies and J labels the other bodies. This is familiar to us. Of course, we are all familiar also with the two-body problem. This is the extension to three bodies. Now, this arose in an idealized treatment of the Sun, Moon, Earth system, as Rashmi mentioned. Perhaps not just Rashmi. I think also Sindhu also joined. Yes. So it arises in an idealized treatment of the Sun, Moon, Earth system and as a toy model for the stability of the solar system. In fact, in the late 1800s, the King of Sweden announced a prize for the study of the stability of the solar system and for somebody who could establish it either way. And several mathematicians and physicists, astronomers presented their work on it, and one of them was Poincare, and he made a lot of progress in this problem. I will describe some of his work. In fact, I should probably tell you about a little anecdote on the three-body problem. Let me just read out what I have on the Longitude Act. The Longitude Act from 1714 of the British Parliament offered 20,000 pounds for a method to determine the longitude at sea to an accuracy of half a degree. So this was important for marine navigation at the time of exploration of the continents. In the absence of accurate clocks that could function at sea, a lunar table, along with the observed position of the moon by the seafarers, was the principal method of estimating the longitude. So that's why this is called the Longitude Act. This is an act of parliament. Leonard Euler, Alexis Clairaut, and D'Alembert competed to develop a theory accounting for solar perturbations to the motion of the moon around the earth. So this is a delightful chapter in the history of the three-body problem. And there is an account of this in an article in Physics Today. I will give you the reference later on. And this includes what I will describe here. The first non-trivial problem, so to speak, to be addressed was the 40-degree per year precession of the lunar apogee. Yeah, so the apogee is the point at which the moon is farthest away from the earth. And it turns out, and this is visible to the naked eye, the moon doesn't quite follow elliptical orbit. The ellipse itself precesses, and over 1 year, the ellipse precesses by 40 degrees. So this is a huge effect. The question was, why does this happen? Newton in the 1680s, of course, he studied the two-body problem and made great progress. He could explain the motion of planets as well as comets. And the next problem was the three-body problem. Newton could account only for half of this perigee precession of the moon, and he gave up after that. And he spent the rest of his life working at the Royal Mint. Clairaut, nearly 50 years later, used what we would call a third-order perturbative approximation to explain 85% of the observed motion of the moon, confirming Newton's law of gravity, which was still in doubt. It was not clear whether Newton's law of gravity is correct or whether you need to change the 1 by r squared to something else. There were lots of ideas there. Yeah. So interestingly, Clairaut's use of Fourier series in the three-body problem predates their use by Joseph Fourier in the analysis of heat conduction. So the three-body problem, right from the beginning, has been a source of ideas in mathematics and physics. One more interesting anecdote I want to tell you. So what I'm reading out is from the article I mentioned in Resonance. Is the discovery of Neptune. The French mathematical astronomer Leverrier in 1846 was intrigued by the discrepancies between the observed and Keplerian orbits of Mercury and Uranus. He predicted the existence of Neptune and calculated its expected position based on its effects on the motion of Uranus, which could be observed around the sun. The existence and location of Neptune was independently inferred also by John Adams in Britain. So soon after, the German astronomer Johann Galle, working with his graduate student d'Arrest, discovered Neptune within a degree of Leverrier's predicted position on the very night that he received the latter's letter. So he wrote a letter saying, go look there and you will find Neptune. And he found it there. Now it turned out that both Adams as well as Leverrier's heroic calculations were based on incorrect assumptions about Neptune. And they were extremely lucky to stumble upon the correct location. So you can discover things even by making mistakes. Okay, so a little bit about three-body problems elsewhere in physics. So the investigation of the three-body problem has stimulated much work in mechanics, nonlinear dynamics, and several areas of mathematics. Yeah, and that was greatly stimulated by Poincaré's work, as well as other dynamical astronomers. There are lots of accounts of this. I would certainly recommend the article by Gutzwiller. I think it's called Sun, Moon, and Earth, the Oldest Three-Body Problem, Reviews of Modern Physics. He also has a book on classical and quantum aspects of chaos. There's also a delightful account by Diaco and Holmes, a book, I think Princeton University Press, 96. So we will view the three-body problem as a model to study and discover novel dynamical phenomena and as a model for chaos. Now variants are also of interest. In atomic and molecular physics, we have the hydrogen molecular ion. So the hydrogen molecular ion consists of two hydrogen nuclei, that is two protons, and 1 electron, because it's been singly ionized. So this is a very simple molecule, very important molecule. If you can show, so there's a pair of protons and an electron. If you can show that this system has a bound state, one state with negative energy, it would explain the covalent bond between two nuclei. This is a very important thing in all of chemistry and astronomy and elsewhere. So the hydrogen molecular ion is an important, and it was quite difficult to handle this. And the study of the three-body problem due to Euler contributed to this problem in quantum mechanics. Euler studied the motion of a test mass in the presence of two fixed gravitating centers, which are not moving. So roughly the two protons are heavy, they are not moving very much. This is called the Born-Oppenheimer approximation. And then you have an electron in their vicinity. So it's a lot like the quantum version of the Euler three-body problem, where you have two fixed masses and a test mass moving around them. There's also the helium atom, of course, which is 2 electrons and 1 nucleus. So that's another very interesting problem. There are other versions. The problem of 3 vortices. So these are line vortices, 3 vortices in a fluid that are moving around. And they are subject to logarithmic potentials. So this problem is quite interested in fluid mechanics. And there is an entire book on it. It turns out to be an integrable system. There's a book on it by Paul K. Newton, who discusses this. There are other versions. The problem of 3 identical bosons, like 3 nucleons or 3 alpha particles, with attractive interactions. This has been studied both in nuclear and cold atom physics. And the Efimov effect, which I will talk about later, comes up over there. There are many other developments. For instance, Faddeev has studied quantum scattering of 3 bodies. And he has set up a system of linear integral equations for 3 bodies scattering, whose solution allows you to describe the scattering. So these are very interesting equations. And also the one that I'm going to talk about more later, which is the 3-rotor problem with cosine potentials. Okay. So let's say a little bit about the classical gravitational 3-body problem. Of course, we start by looking for periodic solutions, and the most famous solutions of the 3-body problem are those of Euler and Lagrange. These are where each mass traverses a Keplerian orbit, a Keplerian ellipse, for instance. So this is remarkable that you can export the solutions of the 2-body Kepler problem to solutions of the 3-body problem. And this idea has versions also in our work. So this is an example, Euler's example, where 3 bodies remain collinear with constant ratios of separations depending on their masses. So it looks like this. So one of the masses is, say, at the center of mass, and the 2 are on either side, and they rotate. So they are always along a straight line. This is another Euler collinear solution. We have the center of mass here and 3 bodies, each of them following a Keplerian ellipse, but always remaining along a straight line. Lagrange extended this to yet more solutions of the 3-body problem, where 3 bodies always lie at the vertices of an equilateral triangle. So this is the picture here. Each body follows a Keplerian ellipse, and the bodies form an equilateral triangle. The size of the equilateral triangle changes with time. It sort of expands and contracts and rotates, of course. Yeah. And these have been used more even recently. I will talk about that briefly. Now, it turns out that Euler's solutions are unstable. I mean, they are periodic solutions, they are unstable to perturbations, whereas Lagrange's triangular solutions are linearly stable if Routh's criterion is satisfied. The sum of the square of the sum of the masses is more than 27 times the sum of products, pairwise products. And this happens, for instance, if one mass dominates. So if you have the Sun, for instance, and then Jupiter and Trojan asteroids, then that would be a place where this may be interesting. Yeah. So the three-body problem itself is rather difficult to solve. It cannot be solved in closed form. We don't have such closed form solutions. We have many examples of periodic solutions. And for that reason, it's interesting to look at special cases or limiting cases. One of them is called the restricted three-body problem. So a useful special case is the restricted three-body problem, where one mass, the primary, one of the M3, this is the planetoid, the small mass is much lighter than the other two. The primaries M1 and M2 follow Keplerian orbits. So M3 doesn't affect the motion of M1 and M2. So for instance, you may have the sun and the earth, or sun and Jupiter in this picture. Jupiter goes around the sun essentially in a circular orbit. And then the third object, which is M3, the locations of possible locations of the third object in Lagrange's solutions in the co-rotating frame of the primaries. Jupiter's going round and round. So you go to that co-rotating frame. In that frame, the possible locations of the planetoid, the third mass, are called Lagrange points. So here you will see L1, 2, 3 are the Euler collinear solutions, where the sun, Jupiter, and asteroid are all along a straight line at all times. So there are three such solutions, the planetoid or the asteroids on the other side, this side, or across from the sun. And then you have two more, the Lagrange equilateral solutions, which are called L4 and L5, or on either side. Yeah. So it turns out that you can work out the sort of effective potential seen by the third body due to the first two. So that includes the gravitational attraction and the centrifugal repulsion, because you're in a rotating frame. And this is that potential is called Roche's effective potential. It turns out that L4 and L5 are at maxima of the effective potential. So naively, they would be unstable. L1, 2, 3 are at saddle points of the potential. So they again would be unstable. But it turns out there's an additional force, which is the Coriolis force, because we're in a rotating frame. And that Coriolis force stabilizes L4 and L5, even though they are at maxima of the potential. So they are potential places to place a satellite, for instance. But it turns out that although the Euler points are unstable, there are small halo orbits around them which are stable. And this has been exploited recently. So the Lagrange points are of interest in space missions. The James Webb Infrared Space Telescope, which is looking at very old and faraway objects, is positioned in a small halo orbit around L2. Okay. So this is the Earth, this is the Sun, and that is the James Webb Telescope of the Sun-Earth system, while our own Aditya solar mission satellite has been placed in a stable halo orbit around L1. So that's always facing the Sun. Yeah, so the Lagrange point is just one point where the satellite, if placed, would be unstable. However, around that, there is a circular or roughly circular orbit. It is a halo in the sense that we think of halo around somebody's head. Yeah. So that's why it's called halo. So it's a small circular or quasi-circular orbit around the Lagrange point. Yeah. And that is where the Aditya satellite has been placed. Okay. Yeah. So one of the messages is that periodic orbits are interesting, and from Poincaré's work, we find that periodic orbits are plentiful in these systems. They're really plentiful. In fact, in systems like three-body or other complicated systems, which are even chaotic, although they may be chaotic, it turns out that periodic orbits are so plentiful that they may even be dense, that near any point in the phase space, there is one point which lies on a periodic orbit. So periodic orbits are quite plentiful, but they are not necessarily the most likely orbit, because they are sort of countable. There are a lot of them, there are infinitely many of them, and they may even be dense, but the typical initial condition does not lead to a periodic orbit. Now, the next slide is about Poincaré's discovery of chaos in the three-body problem. So this is from the late 1800s, 1890s. So Poincaré saw far beyond most of his contemporaries in what he did. This takes a little effort to understand. I will try to make a brief attempt, but let me give you a little bit of history about this. Yeah. So maybe I will tell you about King Oscar's proposal. Yeah, let's try this. So in 1890, in his memoir on the three-body problem, which Poincaré presented to the Swedish Academy, it was the prize-winning memoir. And it was in memory, instituted by King Oscar II for his 60th birthday competition. So, to investigate the stability of the three-body problem, Poincaré defined his surfaces of section, which I will describe in a moment, and a discrete time dynamics via the return map. So Poincaré's surface is a two-dimensional surface in the phase space of your system, and you can imagine trajectories coming and intersecting it. And instead of examining the entire trajectory, you record only the points of intersection. You get a scatter plot that is called the Poincaré surface of section. So a Poincaré surface in this context is a two-dimensional surface in phase space traversed by trajectories, that is transversal to trajectories. The first return map takes a point Q1 to the next intersection Q2 and so on. Now, the interesting story, let me explain it over here. So he defined what are called stable and unstable manifolds of a fixed point. So suppose Q1 is a fixed point. That is, we start there and come back to the surface, you return to the same point. So that's called a fixed point. Now, if that fixed point has a property of being hyperbolic, roughly speaking, nearby trajectories shaped like a hyperbola or like a saddle, then one can ask about nearby points, whether when you iterate them, you come to that fixed point or you go away. If you come, you say that they lie on the stable manifold. If they go away, you say that they lie on the unstable manifold. Don't worry if you don't follow this part, because there's an interesting story coming up. Poincaré was trying to establish the stability of the solar system. There's some prehistory to this, I will explain. But Poincaré assumed that the stable and unstable manifolds do not intersect. This was his assumption, and he, using that assumption, was able to show that the solar system, at least modeled as some kind of three-body system or an n-body system, was stable. So he submitted this to the committee, King Oscar, and it was being examined. And I think Mittag Leffler in Stockholm, and there was another person, Fragman, who you may have heard of from complex variables. They were going through this, and they found an error in this argument, that it was possible for these manifolds to intersect. And this was pointed out to Poincaré, and he realized his mistake, and then he revised his manuscript. Eventually, he got the prize. So Poincaré made a big error in his work, but it turned out to be a very interesting error, and it led to the development of chaos. So it turns out that the stable and unstable manifolds can intersect, and that point of intersection is called a homoclinic point. So these are names given by Poincare himself. Homoclinic means oriented both towards and away. Yeah? Oriented towards a point, fixed point, forward in time as well as backward in time. So he found this concept of homoclinic points, and he discovered something very remarkable, that if the underlying continuous dynamics is in at least 3 dimensions, then if there is one homoclinic point, there must be infinitely many of them which accumulate at the saddle point. And the stable and unstable manifold fold and intersect in a very complicated way around this saddle point, and that structure is called a homoclinic tangle, and this was Poincare's signature of chaos. So this is the first time chaos was glimpsed by somebody. It is not how we see it today. We see it today as sensitivity to initial conditions and other such things, but that is very much here, because near a point which is on stable manifold, if there is also a point on unstable manifold, then nearby things are going to be very sensitive to initial conditions. This in phase space. Yeah, this in phase space. Okay. So, like often happens in science, the first time you glimpse something, it looks very complicated. Yeah. But subsequently, things become simpler. So let me go to more simpler things now. It turns out that new periodic orbits in the 3-body problem continue to be discovered. As I said, they can be plentiful. So, for instance, even 100 years after Poincare and the 1990s, Chris Moore numerically discovered a stable periodic zero angular momentum figure 8 solution. You have 3 bodies, 3 equal masses, separated equally in time. So they are following each other in an infinity-shaped trajectory, equally in time. This kind of solution is called a choreography. You will, of course, recall choreographies from Olympics, synchronized swimming and so on, where the 3 bodies are following each other equally spaced in time. So it was discovered numerically, and then Chensener and Montgomery proved its existence using very nice geometric ideas. And the figure 8 solution also generalizes to other such choreographies, periodic solutions where n masses follow each other at regular intervals around a closed path. So these are examples. There are a whole zoo of such solutions. In fact, let me show you one of those in a movie. Here it is. So this is something like 24 bodies. This is an exact solution of the 24 body problem or so. You can see that, you can see why it's called a choreography. Okay. Another idea that's come out of the 3-body problem is about singularities and collisions. So when 2 gravitating point masses collide or come close by, their relative speed becomes very large because the potential is going to minus infinity. And the solution becomes singular at collision time. Yeah, so that's what we mean by singularity. More generally, a singularity occurs when either a position or a velocity goes to infinity in finite time. So one can ask the question, in a system of 3 bodies or 4 bodies, etc., can a body fly off to infinity in finite time? If it has to go to infinity in finite time, it must have infinite velocity at some finite time. Okay, so that would be a singularity. So Panlave, you may have heard of this name in various areas of maths and physics, and he also became, I think, Prime Minister of France, showed that binary and triple collisions are the only possible singularities in the 3-body problem. Okay? In other words, collisions are the only possible singularities in the 3-body problems. But he conjectured that non-collisional singularities are possible for 4 and more bodies. This seems very strange, but remarkably, after 100 years of work, this conjecture was finally proven in the work of Gerver, Sari, and Shia, who found examples of non-collisional singularities in the 5 body and 3n body problems. So let me describe the example. It's very interesting. So in Shia's example, you have two tight binaries. So imagine two bodies orbiting each other in a roughly Keplerian orbit, another two in another tight binary, and a fifth messenger body that goes between the two. When it comes here, it picks up some kinetic energy from this system and recoils and goes back. While it picks up that kinetic energy, this system falls deeper into the potential and rotates faster, and it kicks out this one and goes there. It goes there, borrows some kinetic energy from this system, accelerates and comes back. So it oscillates between these two tight binaries. In this process, when this recoils this way, the binary recoils this way, and in a finite amount of time, the messenger makes infinitely many oscillations between these two, and these binaries go off to infinity in finite time. So this is a remarkable possibility. Absolutely. How could that happen? Remember that the gravitational potential is minus 1 by r. So when the two bodies in this binary are getting closer, the energy of that pair is becoming more and more negative. And therefore, the kinetic energy can become much larger while the total energy is still fixed. So the potential energy of this pair is going to minus infinity, and the kinetic energy of this is going to plus infinity, such that the total energy is still conserved. Correct. Okay, so in reality, this approximation of point masses will break down at some stage. However, it is not, so this particular example, no, but okay, so asymptotically it will fly off to infinity, but over some range of time, you're still going to see this phenomenon. In fact, there are examples of, maybe not exactly that example, but similar things. So for instance, numerical experiments show that one mass can fly off to infinity in infinite time for the three-body system. That can't happen for finite time singularities, cannot happen in three bodies, but in the three-body problem, one body can fly off to infinity in finite time, in infinite time, while the other two form a bound system, even when the total energy is negative. See, in the two-body problem, if you have negative total energy, then you must be in an elliptical orbit. You cannot fly off to infinity. But in the three-body problem, even with total negative energy, one body can escape to infinity. Now, this may be seen in so-called hypervelocity stars, when one star from a binary is captured by the galactic black hole. So you have a binary and a black hole. One star is captured by the black hole and the other one is ejected and goes off far away, essentially to infinity at a very high speed. So, I mean, there's an article by Brown on this. Okay. So, this was my brief overview of the three-body problem, gravitational three-body problem. I'm just wondering whether I have any other anecdotes to tell you about. Let me tell you one interesting anecdote. So the Finnish mathematician Carl Sundman in 1912 began by showing that binary collisional singularities in the three-body problem could be regularized by a reparametrization of time. So this is some fancy thing to do. That is, near a collision, you could reparametrize time and extend the solution beyond the collision. Why you would want to do that is a separate matter, but while doing that, he found something very remarkable. He used this idea to find a convergent series representation in powers of the 1/3 power of time for a general solution of the three-body problem. So it turns out that the three-body problem admits a sort of analytical solution, but it's not a power series that we are used to. It's not in powers of time. It's in powers of time minus some collision time to the 1/3 power. So it's a very interesting series. It's a convergent series solution of the three-body problem. It doesn't define an analytic function because it's in some fractional powers of time. So, yeah. However, this solution has not been of much use because it is exceptionally slowly converging, and you can find better solutions numerically than using this exact solution. But it looks like Carl Weierstrass, who proposed this problem for Oscar's 60th birthday, had some inkling about the possibility of such exact solutions, and interestingly, Sunman found them. Okay. So, yeah, let me now switch gears a little bit and talk about this three-rotor problem. Okay. Any questions so far? All right. So, in the three-rotor problem, three equally massive point particles, which we'll call rotors, move on a circle without collisions and interact via attractive cosine potentials. So, here's a movie of an example solution. You see, we have three bodies. They move on a circle, and they can pass through each other. You notice they can pass through each other. The dynamics is quite intricate. There's no pattern in this example. Yeah. So if the angular positions of the three rotors are called theta 1, theta 2, and theta 3, then the configuration space is a product of three circles, one for each of the masses. Yeah. I've superposed those three circles on one. And the Lagrangian is simply a sum of difference of kinetic and potential energies. Kinetic energy is simply half mr squared theta dot squared. And then you have a potential energy depending on the cosine of the difference of angles for each pair. Now it turns out that the quantum version of this problem, where you have three rotors on a circle with cosine interactions, governs chains of coupled Josephson junctions. Yeah, I'll explain what a Josephson junction is in a moment. These have been used to model qubits. So for instance, you have, this is a circuit diagram of a qubit with three Josephson junctions. These crosses are Josephson junctions. Each Josephson junction has got a certain Josephson energy as well as a capacitance. Yeah. And in addition, you have some gates in order to manipulate the qubit. So just a quick statement about what a Josephson junction is. So a Josephson junction is a thin insulating layer or a non-superconducting layer between two superconducting metallic segments. Cooper pairs from the superconducting segments can tunnel across the barrier. See, this is insulating. So ordinarily you would think that electrons cannot pass through, but they can tunnel across, and this was Josephson's discovery, without resistance. And the system as a whole, the pair, functions as a non-linear inductor. So you remember that in an inductor, you have the voltage current characteristic, V is equal to L di by dt. But if the inductance itself depends on the current, it becomes a non-linear inductor. So Josephson junction behaves like some kind of non-linear inductor. Now, each of the superconducting segments can be described by a superconducting phase. This is the so-called Ginzburg-Landau phase of the macroscopic quantum wave function, so to speak. So each of the segments is described by a phase, 0 to 2 pi phase. And at each junction, you have the phase difference, which is called the Josephson phase. Now, the rotor angles that I was talking about in my previous slide, theta 1, theta 2, theta 3, are precisely the superconducting phases in the three metallic islands. Now, the potential energy is the Josephson coupling energy across the junction, and that can be shown to be some Josephson energy times the cosine of the difference in angles. So that is precisely the energy we had previously. So the Josephson coupling energy is the same as our coupling constant in the previous slide. We had this coupling constant G. Now the kinetic energy is a capacitive charging energy of the junction. So half capacitance times potential difference squared, and Josephson's equations help you calculate what that is. So Josephson tells us that the voltage across this tunneling junction is given by the rate of change of the relative phase between the two segments, phi dot. So if you square that, you're going to get a phi dot squared, and that starts looking a lot like these theta dot squares. Okay, you have to rewrite things a bit, but I've tried to indicate to you why a chain of coupled Josephson junctions is actually modeled by a system of rotors. The current is given by some critical current times the sine of the angle. If you sort of combine these two equations and eliminate the angle, you will discover a nonlinear voltage current relationship. Yeah. It turns out that the junction capacitance is related to the mass of our rotors. So there is a mapping between this mechanical system of rotors and the Josephson junction system. Furthermore, the rotor angles, as we said, correspond to phases at distinct sites. These are at distinct sites. They are distinguishable sites. And there is nothing wrong with the Ginzburg-Landau phase in this site being the same as in that site. Okay, they are different sites. That is why the rotors can pass through each other without any collisional singularities. So in our movie, we saw the red and blue rotors passing through each other. That's because they represent phases at distinct sites. Furthermore, it means that the rotors are distinguishable particles. Here they have equal masses, so they are identical, but they are distinguishable. Okay. So this is one interesting connection of the three-rotor problem. It also is connected to another problem, this time from, that one was from low temperature physics. This is in statistical mechanics. This is a slightly different connection, related of course. So the quantum n rotor problem, see we were talking about 3 rotors, but you can have n rotors as well, 4 or 5, etc. It also arises from a partial continuum limit of the so-called XY model of statistical mechanics, classical statistical mechanics. So in this model, you have a lattice, indicated a rectangular lattice here. At each point of the lattice, you got a spin, which is restricted to the plane. Yeah, so that's why it's called XY. So the spin can point in any direction at that point in that plane, and it is subject to ferromagnetic attractive interactions. So if you have the spin at site ij and the spin at I prime j prime, neighboring sites, then the interaction is given by the dot product of the spins, which if you write in terms of modulus argument, you will find it is the cosine of the difference in angles. So you begin to see why this may be related to the rotor problem. Now, if we take a interesting continuum limit where we let the vertical spacing B be small, make this spacing small, while keeping the horizontal spacing fixed, and take a certain continuum limit, then the interaction energy just becomes our theta prime squared. Yeah, the interaction energy in the vertical direction, if you change the vertical direction into time. So this is called Wick rotation. If you do a Wick rotation, then the vertical direction becomes time, and the interaction energy in the vertical direction becomes the rotor kinetic energy, and the interaction energy in the horizontal direction becomes the potential energy of rotors. So it's possible to do this. So our model is related to the XY model of classical statistical mechanics, and this model is quite interesting for independent reasons. The XY model displays the so-called Kosterlitz-Thouless topological phase transition, and they got a Nobel Prize for this about a decade ago, and it has very interesting features. And we were actually trying to understand their work, and in the process of doing that, we found an interesting problem to study. Okay, so let me say a little bit about this classical three-rotor problem. So we can view the classical three-rotor problem as a simpler variant of the gravitational three-body problem. It's simpler because the configuration space is a circle, particles move in a circle, whereas in the gravitational one, the whole of Euclidean space. So it's compact. And the potential is bounded, it's just a cosine potential rather than 1 over r. So it's simpler in that sense. There is no infinity for particles to escape because everything is going around a circle, nor can the dynamics produce any singularities. Rotors can pass through each other. But you can turn around this simplicity to our benefit. These features, that is, there is no escape to infinity, there are no singularities, they are actually conducive to the development of chaos. Because if you have complicated behavior in a bounded region, that is conducive to the development of chaos, yeah, if instabilities are present. Okay. So it turns out that the problem of two rotors reduces to the simple pendulum. After all, the simple pendulum involves a cosine interaction. So it's not surprising that two rotors is a simple pendulum. While on the other hand, if you have infinitely many rotors, you can take a continuum limit, and that system is described by the so-called sine-Gordon field. In both of these limits, there is a sort of simplicity. The sine-Gordon field is an integrable model, and so is the pendulum. But between these extremes, we find that three rotors display very rich dynamics. And that should carry over to 4 as well as 5 rotors. So we use it as a place to study periodic orbits, instabilities, bifurcations, the onset of chaos, ergodic behavior, and quantum manifestations of chaos. So I will tell you a little bit about these things. Yeah. Any question? Okay, so just like in gravitational two-body, three-body problem, it is convenient to define a center of mass and relative variables. So you define a center of mass angle, the sum of the angles, and then the differences, phi1 and phi2 are the differences. Now it turns out that the relative angles, phi1 and phi2, evolve independently of the center of mass angle. So you can eliminate the center of mass motion, which just governs a rigid rotation of the whole system. Yes, so you got here the equations of motion of the relative angles. Phi1 double dot and phi2 double dot are given by rather nonlinear functions of the relative angles. Okay, so in the gravitational problem, you had some 1 by r squares and so on. Here you have some trigonometric functions. So here I plot for you the phi1 and phi2 are angles. Okay, so they have defined modulo 2 pi. So the configuration space in the relative motion is given by a torus. So the angle around this cycle of the torus is called phi1, and around that cycle of the torus is phi2. So you got motion on a torus. And I've plotted a few trajectories here. So you see some rather interesting trajectory here, which is, I would call a regular trajectory. There's a pattern to it. And here, a chaotic trajectory where you don't see much of a pattern to it. Now it turns out that relative energy, that is aside from center of mass motion, the relative energy in units of the coupling is the only known conserved quantity. Yeah. So you have a system with a two-dimensional configuration space, two-dimensional configuration space, four-dimensional phase space, and only one conserved quantity. So you have the total energy of the rotors, which is given by this, if I put a plus sign here. This is the total energy. That total energy can be written as a sum of contribution from center of mass motion, phi zero motion, and relative motion. I am removing the center of mass motion. Yeah. So here we are. The relative energy, as you were asking, is given by this formula. It involves only the relative angles. Phi1 dot squared, phi2 dot squared, a cross term phi1 dot, phi2 dot, and all these cosine interactions. So it turns out that the system for the relative motion has some simple solutions, which I will call static solutions. The ground state is when all the rotors are at a common point, common angle. in the magnetic or statistical analogy, this corresponds to 3 rotors or 3 spins which are all pointing upwards. So this is a sort of ferromagnetic ground state, you might say. There's another static solution where 2 rotors are diametrically opposite from the third, fixed at all times. Yeah. So that is a little bit like saying that up, down, up. Up, down, up, the 3 rotors. So that's a little bit like the anti-ferromagnetic ground state for 3 bodies. And then you have another solution where 3 rotors are at vertices on an equilateral triangle in this circle. So that's a bit like spins that are changing angle a little bit as you go around. It's a little bit like a spin wave, you might say. So these are the static solutions. The ground state is at the minimum of the potential, and these other 2 are at local maxima and saddle points of the potential. Now the system behaves regularly as the energy goes to 0. For low relative energies, you have small oscillations around the ground state. When the energy is much less than the coupling, you have small oscillations around the ground state, and you have 2 conserved normal mode energies. 2 degrees of freedom, 2 conserved quantities, so the system is solvable. That's true only at very low energies. Similarly, at very high energies, the kinetic energy dominates over potential energy, and in that limit, the 2 relative angles both become cyclic coordinates, and again you have 2 conserved angular momentum. So at low and high energies, the system is integrable, solvable. But we will see that interesting things happen in between. So let's see this in a picture first. So these are the so-called Poincare plots or Poincare surfaces of section. We have this 4-dimensional phase space. We fix an energy. So that reduces to 3 dimensions. So that 3 dimensions is like this room. Within this room, we put a plane. And we follow trajectories, phase space trajectories in this room. Fixed energy trajectories. And ask where they intersect this surface. We record the points of intersection in time. At low energies, it turns out that the trajectory comes, intersects, goes behind, comes back, intersects. So this is a scatter plot, but if you do it for a long time, you will see some patterns. But at low energies, 3.5 for instance, in units where G is 1, you see very regular behavior. The trajectories are all concentrated on closed curves. The Poincare plot is concentrated on closed curves. We call that regular behavior. So the trajectories in the full space would either be periodic or quasi-periodic, that is having 2 incommensurate frequencies. That is still regular. However, once you reach an energy nearing 4, one starts seeing the scatter plot starting to occupy 2-dimensional regions. Here they were all concentrated around curves. Here they start spreading out. And as you increase the energy, they spread out even more. So these are the chaotic trajectories, like the one I plotted before. These chaotic trajectories intersect the Poincare surface over an entire 2-dimensional region. And that region occupied by the chaotic trajectories keeps growing as the energy increases. So at energy 5.5, practically any initial condition will lead to a trajectory that fills up the whole Poincare surface. So this is an indication that the system is becoming very chaotic, perhaps even globally chaotic. But as the energy increases further, say energy 10, so this happens around energy 4 to 5, but as the energy becomes higher, one starts seeing regularity return. We see some islands of stability or some periodic and quasi-periodic orbits re-emerging. And asymptotically high energies, we again go back to something like we had at very low energies, where you have a lot of regular behavior. There may be patches of chaos here and there. So we can call this an order, chaos, order transition or crossover. Yeah. So this is a system that has this feature. As this transition happens, various interesting phenomena also happen. For example, there is a spontaneous breaking of certain symmetries of the original Hamiltonian. The original Hamiltonian had some nice symmetries. They are present at low energies, and some of them are present at very high energies as well. Some left-right symmetries, up-down symmetries, that kind of thing. But they are not preserved when you are having this transition to chaos. So you have some kind of spontaneous breaking of symmetries. But the chaos is also quantified in other ways. One can study how two trajectories that begin nearby, how they behave over time. Do they stay nearby? Do they oscillate between each other? Do they get apart? Do they get apart linearly, or do they get apart exponentially fast? This is quantified by what is called the Lyapunov exponent. That is a measure of exponential divergence of trajectories that begin nearby. So one can make this idea quite precise. Even though our configuration space is compact, it is possible for us to talk about exponential divergence while remaining inside that. Yeah. So if people are interested, I can explain this some other time later on. But one can quantify this exponential departure. The distance between two trajectories goes like exponential of some constant times the time. That constant is called the Lyapunov exponent. And if that constant is positive, it means exponential divergence. So here I have plotted the largest Lyapunov exponent as a function of energy for various initial conditions. One finds that at low energies, the Lyapunov exponent is 0. So there is no exponential divergence of trajectories. However, once the energy reaches 4 and increases, one sees positive Lyapunov exponents, which signifies sensitivity to initial conditions, nearby initial conditions going rapidly apart. And as I was saying, there is some global chaos around energy 5 or so, where the Lyapunov exponents become pretty large. And as you go to higher energies, they come down gradually. So you are again seeing order, chaos, order behavior. So in this, we also find a globally chaotic band, as I was describing before, in a range of energies between 5.33 to 5.6, where the fraction of chaos is roughly 1. What do I mean by the fraction of chaos? You look at a Poincare surface and measure what portion of it consists of chaotic trajectories and what portion regular trajectories. So suppose you calculate that and plot it here. The fraction of chaos is roughly 0 up to energy 4. Then it shoots up all of a sudden and reaches practically 1. So the whole phase space is filled with chaotic trajectories. And that is the regime of global chaos. Why is global chaos interesting? If we are interested in study of gases or molecular dynamics of complicated systems, following Boltzmann, Gibbs, and others, we want to use statistical mechanics, thermodynamics. And what lies at the basis of Boltzmann's work is the assumption that the system behaves ergodically, that you can replace time averages by phase space averages or ensemble averages. Now, one would like to establish is this in model systems, that model systems have this ergodic behavior, and if a system has global chaos, then it is a good candidate for ergodic behavior. So this is a phase of global chaos where I've shown various Poincare surfaces, and you see almost uniform scatter plots of chaotic trajectories. And we have looked at the ergodicity in these band of global chaos. We have shown that the dynamics is ergodic, at least conjecturally, as well as mixing on each energy hypersurface. So for instance, here we plot as a function of energy the difference between a time average of an observable and the phase space average of an observable. We take this difference and plot it. If the dynamics is ergodic, this difference should be 0. So if you look at it as a function of energy, so this is some square of some relative angle. Yeah. In the band of global chaos, around 5, energy 5, the difference is essentially 0, up to errors. Whereas when you go outside that energy band, the difference is non-zero. So you see that there is ergodicity in that regime. uh, yeah. And let me show you, there's a nice movie here. The motion is also mixing. And what does that mean? 1 second. I have lost. Yeah, let me restart this movie. Okay, so here we are. So I've taken an energy, fixed energy, so that our 4-dimensional space has become 3-dimensional by fixing energy. Within that 3-dimensional space region, I pick a bunch of initial conditions within a small volume. Okay. So that small volume is my set of initial conditions. The energy surface is compact, so I've represented it by a cube out here in suitable coordinates, and one finds that if you evolve forward these initial conditions in time, they basically fill out the whole of the energetically allowed phase space practically uniformly. So this is a lot like the way ink, when put in a turbulent fluid, mixes all over the fluid. Okay, so that is called mixing. There are precise definitions of this, but we do see a graphic example of the system displaying mixing. Yeah. So, okay, I should pay attention time as well. So what are we? Okay, yeah. You are welcome to discuss with me even now or ask questions. Yeah, okay. So let me go on to some more things. So the system displays very interesting features. I want to describe a certain geometric observation we have made. And this is a general result about mechanics. Yeah. So we know that free particles follow straight lines. Yeah, this is Newton's first law. In an inertial frame, free particles follow straight lines. Straight lines are also geodesics of the Euclidean geometry. So one wonders whether even in the presence of forces and potentials, the trajectories, Newtonian trajectories of a body can be described as geodesics of some geometry. Okay. So this idea goes back to the study of Maupertuis and Jacobi later on, who found out how, Euler as well, they found out that for any fixed energy, the trajectories of a mechanical system, Hamiltonian system, can be realized as a geodesics of a certain metric or a geometry. That is a metric or a geometry on the configuration space. So that metric is very interesting. If you have a Lagrangian of this sort, it's some kinetic term with some coefficients and some potential energy. Then one defines a metric tensor, Gij, in components as basically the coefficients coming from the kinetic energy times the energy minus the potential. So this is some function of the positions, and this defines a Riemannian metric on the configuration space. And one can look at the curves of shortest length or geodesics in this geometry. And Gauss and Riemann have taught us that the curvature of a geometry, the curvature of a metric, tells us whether two neighboring geodesics oscillate. That is called positive curvature, such as on a sphere. On a sphere, great circles are our trajectories, great circles are our geodesics, and great circles simply oscillate. Yeah, you may have one great circle on one equatorial plane and another on a slightly different plane. The distance will oscillate. And that's called positive curvature. You could have negative curvature, such as on a saddle or on a hyperboloid, where nearby geodesics exponentially deviate, and zero curvature, like on a plane, where straight lines linearly depart. Okay. So the reason this is interesting in chaos is that chaos is about instabilities, nearby initial conditions being very sensitive, trajectories based on nearby initial conditions being very sensitive to those initial conditions. That is, they go apart. So if you can establish a relation between trajectories and geodesics, which is what Jacobi and Maupertuis did, they have shown us that Newtonian trajectories are simply reparametrized geodesics of a certain metric. Yeah. And if you compute the curvature of that metric, it will tell you whether these trajectories are stable or unstable. In the three-rotor problem, we have carried out this idea, and we find that for energies less than 4G, yeah, this energy 4 was quite interesting because up to energy 4, the motion is rather regular, and beyond energy 4, it becomes chaotic. That is somehow connected to the curvature of this metric. It turns out that when energy is less than 4G, the curvature of the Jacobi-Maupertuis metric is strictly positive. So here is a plot of the curvature, it's called Gaussian curvature, on the configuration torus 5152 space. The curvature is always more than 0. But when the energy exceeds 4, the curvature takes both signs. Some places it's negative, some places it's positive. So this mixture of positive and negative curvature means that in some places trajectories are focusing, some places they are diverging, and that's a signature of this instability and chaotic behavior. So there are not many example systems where there is such a close connection between these geometric notions of instability, geodesic instability, and chaos. So we have one of those. Okay. Another very interesting phenomenon we have seen in this system, I want to describe to you. As I was saying, it is interesting to study periodic solutions. In any dynamical system, we first start with static solutions and then we go to periodic solutions. So just like Euler and Lagrange did, they discovered periodic solutions of the three-body problem starting from periodic solutions of the Keplerian two-body problem. Okay, this idea. So we've carried out this idea now in the three-rotor system and found families of periodic solutions of the three-rotor system starting from solutions of the two-rotor system. These come in two varieties, which I will call pendula and breathers. So what are pendula? In pendulum solutions, two rotors form a molecule and the third rotor oscillates about it. So here it is, a movie of it. Two of the rotors have formed a molecule, they are zero separation, the blue one, and the third rotor is the yellow one, and they oscillate like a pendulum. The equations are those of a pendulum. Okay, so this is called a pendulum solution. It exists at all energies. If the energy is less than 4, it looks like that. If the energy is more than 4, it becomes a rotational pendulum. So you will recall what a pendulum is. This is a pendulum. It's called librational pendulum. But if you give the pendulum more energy, it can go all the way up and come down, right? So that's called a rotational pendulum. And we see that here too. The blue one is the molecule consisting of two rotors, and then you have the yellow. And this is a rotational orbit. So there are orbits at all energies, pendulum-like orbits from energy 0 all the way to infinity. So you have a family of periodic orbits. Yeah. Now there's also the so-called breather solutions where one rotor is permanently at the center of mass between the other two. So the blue one is between the other two, and the red and yellow one oscillate about it. So this is another family of periodic orbits, and they exist at all energies as well. So you should roughly think of these as some kind of analogs of the Euler and Lagrange solutions of the three-body system, but now for the three-rotor system. But something absolutely remarkable happens with this family of solutions, the pendula. So I will tell you about that. Okay. So I'll explain it in this picture. So just like we can ask about the stability of a static solution, that is, you have some solution, you make a small perturbation and ask whether it comes back or oscillates around it. Then you will call it stable. If you make a perturbation and it wanders away, you will call it unstable. The same question can be asked about periodic solutions as well. You have a periodic solution like this circular orbit, you make a small perturbation and watch what happens to the perturbation. If it sort of oscillates around the original trajectory, it would be a stable trajectory. Now, that stability of a periodic orbit is encoded in a gadget called the monodromy matrix. It's a simple idea. A monodromy matrix tells us if you start with a perturbation, let it evolve over one period of the original orbit, it will return to some new perturbation after the full period. The monodromy matrix tells you how this vector is transformed to that vector. Okay, so it's simply a matrix that sort of rotates and stretches. The eigenvalues of this matrix will control the stability. If it gets stretched a lot, then it will be unstable. And that will happen if the eigenvalues of the monodromy matrix are more than 1 in magnitude. If there is one such eigenvalue more than 1 in magnitude, you will have instabilities. If all the eigenvalues are phases, then you will simply oscillate. The vector will simply rotate a little bit. Okay? So it turns out that the stability can be encoded in the trace of the monodromy matrix. It turns out the monodromy matrix in this case is 4 by 4 matrix because it's a 4-dimensional phase space. 2 eigenvalues are always equal to 1, so they are less interesting. The other 2 eigenvalues are of the form mu and 1 by mu. This is because, roughly speaking, this is a Hamiltonian system, and if you have one stretching direction, there will also be one contracting direction, because Liouville tells us that the total phase space volume is conserved. Based on that, if you have an eigenvalue mu, there will be, which is more than 1, there will be one that is also less than 1, but the sum will always be more than 2. On the other hand, if the eigenvalues are phases, their sum, which is the cosine, is always less than 2. So the upshot of all of this is that if the trace of the monodromy matrix is more than 4, 2 are always 1, 2 more, sum to more than 2. If it's more than 4, you have instabilities. If it's less than 0, again you have instabilities. Between 0 and 4, the trace is between 0 and 4, it's stable. So now let me tell you what one finds. This is a very interesting phenomenon. I told you that the pendula are a family of periodic orbits. They exist at all energies. So the horizontal axis is the time period of the pendulum orbit. With increasing energy, you have the liberational pendula. And those are the rotational pendula, where you start with infinite energy and come down. Come down. Okay. Now we'll study the stability of these pendulum solutions. We find something very interesting. At very low energies, the liberational pendula are stable. Then all of a sudden, you find an energy or a time period at which the pendulum becomes unstable. Then again it becomes stable over a window of energies. Then all of a sudden it becomes unstable over a window of energies. We are seeing stability transitions in a family of periodic orbits. And this pattern repeats infinitely often. The dividing line between libration and rotation is where the time period of the pendulum goes to infinity. I mean, this is a simple result from pendulum studies. The time period of pendulum glows with amplitude, and as the amplitude reaches all the way to the top, the time period goes to infinity. So what we find is that there is a succession of stable and unstable windows as the energy is increased, infinitely many of them, that are periodic in a log scale in energy or in a linear scale in time period. And these stability transitions accumulate at the libration to rotation threshold. So the main message is that there is an infinite sequence of sort of phase transitions or stability transitions in this system, accumulating remarkably at the same energy roughly where global chaos sets in. So there's some connection between these accumulation of stability transitions and the development of chaos. We don't understand deeper reasons for this. Yeah. Yes. Yes. Yeah. So, see, first, okay, please finish your question. Okay. Okay, let me try to address this. Let's go back to the ordinary simple pendulum we study in mechanics. This is the oscillation. It has a certain energy. Now, as the amplitude increases, the energy increases. When the amplitude reaches a point where the trajectory can go all the way around, the energy has not gone to infinity. Energy has reached something like 2 mgl. Yeah, if the energy is 0 here and mgl here and it's 2 mgl there. So the energy reaches some critical value, but at that stage, the time period has gone to infinity because it takes longer and longer for the pendulum to go up and come down. Yeah. So that's the divergence in time period I'm talking. The energy is not diverging. Energy is finite. So the pendulum takes longer and longer to reach the top because it's slowing down, becoming very, very, very slow and never actually reaches the top. But if you give the energy 2 mgl, it will just reach the top. If you give more than 2 mgl, it will cross the top and come around. That's called a rotational pendulum. That again will have very large time period. Yeah. And then as it goes, give more and more energy, the time period will actually decrease because there's a lot of kinetic energy. It will spin around very fast. So the center of mass doesn't have much relevance to this. Yeah, in our system, we have actually removed the center of mass motion. I hope that addresses. Yeah. So, okay. So this is the phenomenon that we see, and it has some connections to various other problems. Perhaps I will mention a couple of them because it connects to various different types of physics. For instance, it is related to solid state physics. Yeah. See, what are we doing here? We are studying perturbations to a periodic orbit. You can think about a periodic orbit as the analog of a periodic potential in a crystal lattice. And Bloch studied this problem, electron motion in a periodic crystal. And what you find over there is that there are forbidden energy bands and allowed energy bands, which is a foundation of the band structure. So our stable and unstable windows of energies are a lot like the allowed and forbidden energy bands for an electron in a periodic potential. Yeah. There are also connections to nuclear and molecular physics. This is a very remarkable phenomenon that Efimov found in the 70s. So Efimov studied the quantum spectrum of three alpha particles, for instance, subject to attractive interactions. Now he's studying this in a special limit. One moment. So he studied this in a limit where the S-wave scattering length is much larger than the interaction range. So this is low energy scattering. You have studied the partial wave expansion in scattering theory. One may recall that at low energies, S-wave scattering dominates. That is because at low energies, when I say low energies, low wave numbers, the angular momentum classically is bounded. You can put a bound on it using simple mechanics, using the impact parameter and the incoming velocity. So if the incoming velocity is not too large for a given impact parameter, the energy is low, then you can infer that the angular momentum cannot be very large. So at low energy scattering, it is S-wave scattering that dominates, and the scattering amplitude, which comes up in partial wave expansion, the limit of the scattering amplitude at low energies, zero wave number limit, is called the scattering length. Okay? It's called the S-wave scattering length. So scattering length has a simple interpretation also. At low energies, the scattering cross section is 4 pi times the square of the scattering length. Okay? So it is some kind of measure of the size of the obstacle as seen by the potential. And as long as that is much larger than the interaction range, that was the limit that he was studying, he found something very remarkable. He found that there are 3 body bound states. We are studying 3 nucleons. He found several 3 body bound state energies. These are called trimers, a spectrum of trimers, and that they form a geometric sequence, the energies, and those energy levels accumulate at the zero energy threshold corresponding to arbitrarily weak 2 body bound states with this diverging S-wave scattering length. Well, there's a lot of words here, but what we're saying is that in this limit, 2 body bound states are arbitrarily weak, but there are still 3 body bound states. Okay? So no 2 bodies can be in a bound state, but 3 together can be in a bound state. It's amusing. There's a kind of cartoon for this called the Borromean rings, where you have 3 rings where no 2 are interlinked, but the 3 together are interlinked. So it's like a cartoon of the kind of thing that's happening here, where you have 3 body bound states without any 2 body bound states. But this phenomenon, though it's in the quantum theory, the accumulation of these levels is similar, in a vague sense, to the stability transitions, the accumulation of stability transitions in 3-rotor pendula. And the divergence of the scattering length is analogous to the diverging time period that I spoke about. There are other examples of this in other dynamical systems. One of them comes from galactic physics. The Helmholtz system is a model for motion of a star in a galaxy, near a galactic center. And Helmholtz developed a simple model for this. It's a 2-dimensional model, XY, and it involves a x squared and y squared harmonic type energy, but also some cubic energy terms like x cubed and xy squared. So in this system, which models star motion in a galaxy, they discovered what are called a family of periodic orbits, which they call the A family. And that family also suffers this sequence of stability transitions. So there is some similarity to what we have here. Okay. Now something interesting happens at these stability transitions. So this is probably, this now connects to yet another branch of physics, bifurcations. So at these stability transitions, something very interesting happens. And they are called bifurcations. So let me tell you what a bifurcation is. So a bifurcation is a qualitative and sudden change in the dynamics of a system as a control parameter like a mass or coupling constant is continuously varied. So this sudden change could be the loss of stability of a family of solutions or the morphing of a static solution into a periodic solution or other such things. So let me give a simple example. The buckling of a card under compressional stress F is an example of a bifurcation. So imagine a card like this one, and you are applying a force on it from either end. For small forces, the card remains flat, the flat card. So there is only one equilibrium, it's a flat card. But if the force exceeds a critical force, you press very hard, you see that the card either bends one way or the other. So you have this card bent upwards or the card bent downwards, in addition to the straight card. That's also there, it's an unstable solution. So this is an example of a bifurcation where at a critical force, the flat card solution splits into 3 solutions, 2 of which are stable and 1 is unstable. So this is an example of a bifurcation, and this is a bifurcation diagram. Now, such things come up in other dynamical systems. Perhaps the most famous of these is the logistic map. Some of you may have heard of it. Let me just remind you or introduce you to it. The logistic map, which is one of the most famous discrete time dynamical system models the population of a species at the nth time step. So suppose you have a family of insects and a collection of insects, their population is xn in some units. And the population at the next time instant is given by the r times xn times 1 minus xn. So this tells you what the population at the next instant is. For small x, you can ignore this quadratic term, and r is simply the growth rate. But you can't simply have growth, there are also finite resources. So this quadratic term, negative term, quadratic term inhibits growth. So there is some possibility of balancing over here. This system was studied, for instance, by Feigenbaum, who thought of it as a simple model for turbulence in hydrodynamics. For small populations, for small growth rates R, what you find is that as you iterate, take n larger and larger, the population reaches an asymptotic value, some value, and there's some number of insects. But if the growth rate increases a bit, so this is that asymptotic value. But for larger growth rates, asymptotically, the population oscillates between two stable values, 100 insects and 140 insects. That's what this is. At some critical growth rate, there is a bifurcation from a fixed asymptotic value to two values. So you have a period 2 solution which becomes an attractor for the dynamics. Any initial condition will tend to that periodic solution. At even larger growth rates, each of those branches bifurcates yet again, and there is this cascade of bifurcations repeating itself. They are called period doubling bifurcations. A period 2 orbit splits into a period 4 orbit, and so on. And in this case, it turns out that the windows between one bifurcation and the next, the ratio of those window lengths is asymptotically a constant called Feigenbaum's constant, and he estimated and calculated it. It is a kind of a universal quantity in many such dynamical systems. So I want to draw the attention or the analogy between this geometric cascade of bifurcations in the logistic map and our cascade of stability transitions in the 3-rotor system. There is at least a qualitative similarity. So in our system, what happens at these bifurcations is very interesting. So let me go back to our figure. I am increasing the energy. The pendulum family is stable. Then it hits a bifurcation where it becomes unstable. At the bifurcation, the pendulum periodic solution gives birth to a new periodic solution. So this is another bifurcation where the pendulum family continues to exist. It was stable here, then it becomes unstable. But at the bifurcation, a new family of periodic solutions is born and has its own evolution. So that family continues to exist. It is stable for some regime and then becomes unstable. And this happens at every such stability transition. It turns out when the trace of the monodromy exceeds 4 or hits 4, we have what are called isochronous bifurcations, where the period of the newly born orbit is the same as the old orbit, the pendulum orbit, whereas at trace m equal to 0, the bifurcations are period doubling. That is, the orbit that is born, the newly born orbit, has twice the period of the pendulum orbit. This was roughly 8, it's become 16. So in some way, these bifurcations are a way of generating new periodic solutions from old ones in a very interesting and novel way. So this is, and you can look at the shapes of the newly born orbits. They, at each bifurcation, you have a new periodic orbit that's born. We have developed a nice technique to find these orbits numerically, a search algorithm. And one can see that at successive bifurcations, let's take this one, the period doubling first bifurcation and period doubling second bifurcation. The orbits look somewhat similar, but they have an extra oscillation. Yeah, so these are roughly like successive excited state wave functions in a quantum system. I mean, this is a classical system, but I'm just drawing an analogy that at successive bifurcations, you get more oscillations in the orbits. So similarly, this orbit and that bifurcation has developed an extra oscillation. So there's actually a precise connection in the equations. So anyway, this model is very rich and has allowed us to study these bifurcations in some depth. Yeah. So in fact, there is an analog of even Feigenbaum's studies over here. It turns out that there is a scale invariance or self-similarity in this system. If you go near the energy 4 and zoom in, you will see what you see previously. So I'm plotting here the trace of the monodromy. You have the newly born orbit at the first isochronous and second isochronous bifurcation. When this is 3.995 and 4, we zoom in 3.99995 and 4, we see the third isochronous and the fourth isochronous bifurcation. And the picture is essentially the same as the old one. You zoom in yet another time and you see the fifth and the sixth. And there is a asymptotically constant magnification factor, and that is an analog of the Feigenbaum scaling exponent, and we have estimated it for our system. It is the exponential of root 3 pi. Yeah, and so there is self-similarity and scaling constants that one can study in the system. Okay, so I think I have discussed many things about this classical three-rotor problem. The importance of periodic orbits and how they are, how the instability or stability of periodic orbits may somehow be connected to the development of chaos. The connection is not clear to us yet, but there is something there. More recent work has concerned the quantum mechanics of this system, but I'm probably running out of time. So let me see. Yeah. Sure. Yeah. Yeah, I mean, this is because the next part is on the quantum system. So perhaps I will not go there right now. Yeah. I mean, I can sort of conclude. Yeah, perhaps I can just briefly discuss some of the things. So besides their application to celestial mechanics and chains of coupled Josephson junctions, we have viewed the three-body and three-rotor problems as places to discover new dynamical phenomena, bifurcations, chaos, stabilities, instabilities, and study aspects of chaos and bifurcations. We have shown that the presence of widespread geodesic instabilities in the three-body problem, we have shown the widespread presence of geodesic instabilities by evaluating the curvature of the Jacobi-Maupertuis metric. And in the three-rotor problem, we find that the transition to widespread chaos in the classical three-rotor problem is associated with several striking phenomena. One, a sharp rise in the fraction of chaos on Poincare surfaces, largely positive Lyapunov exponents, spontaneous breaking of discrete symmetries, an accumulation of stability transitions and fork-like bifurcation. They are fork-like because you had a family of solutions and it splits into two families of solutions. So it's like a fork. Fork-like bifurcations in the pendulum family of periodic solutions, a change in the sign of the Jacobi-Maupertuis curvature. There's also a change in topology of the energy, allowed energy region called the Hill region, and a deeper understanding of the interconnections among these phenomena is desirable. The quantum version, we have several results which I have not discussed, but there are deep connections between the classical theory and the quantum theory. In particular, the periodic orbits of the classical theory can be used to make predictions semi-classically of what to expect in the quantum theory. So that is something that we are working on, to use periodic orbits and their properties, their time periods, their stability. Yeah, everything from the classical theory can be put together in very interesting ways. This is an idea that goes back to Gutzwiller, to make predictions about the quantum theory. Okay. So my message is that the classical theory is very deep and rich and has applications even to understanding the quantum theory. Okay, so perhaps I will stop there.
Nice talk. My question is regarding the Poincare map. As I understand, you reduce the dimensionality of the phase space by energy, constant energy constraint. And in that three-dimensional cuboid, my question is, can you take any plane as the point? I mean, if I tilt the plane, will I get the same map? Not in shape, but in terms of regularity and chaotic behavior. That is my question.
Yeah, it's a pertinent question. Yeah, so once you fix the energy, you reduce the phase space dimension by 1. So if you started with 4, it becomes 3. It's like this room. You can choose many surfaces. It need not even be a plane. It can be some wavy surface. Yeah, each of these surfaces will capture different features. However, for instance, if you have some globally chaotic regime, no matter which surface you pick, you get similar qualitative features. Even in the regular regimes, here we pick the surface phi1 equal to 0, and the pattern looks like this. If you choose a slightly different surface, the pattern won't look so symmetric, maybe a little crooked, yeah, but qualitatively it will be similar. That is certainly true. For instance, even if you calculate the fraction of chaos as a function of energy, it is not sensitive so much to the choice of the surface. So you are right. But details do matter. The choice of surface, details do matter. But some gross features are common.
Thank you. Another, if I have time, just an amusement, because the same kind of chaotic behavior is seen in many systems like double pendulum, quartic oscillator, or oval, what do you call it, billiard ball table, etc. All of them generate the same kind of map. But then the question is that is there something very deep underlining connection between all these kind of systems dynamically?
Yeah. Okay. So one hopes that there is something deep connecting these systems. So for you are quite right. You mentioned the 3 systems. One is the double pendulum, which is not so different from this, in the sense that even in the double pendulum, at low energies the motion is regular. At very high energies, the 2 pendula simply go around. So there too you have this order chaos order behavior. Yeah, and the other one you mentioned was billiards. Am I right? Chennai billiards or other stadium billiards. Correct. Yeah. So of course that's slightly different because you have specular reflections across at the boundaries. Now, so these are all different systems. It would be interesting to know if there is some common features. Yeah. What common features might there be? For instance, could it be that periodic orbits in all these systems are plentiful, perhaps even dense in the energy manifold? So that is one feature that may be common. There may be other features that are common. So I described some scaling constants that one can calculate associated to certain bifurcations. One could ask whether those scaling constants are system dependent or system independent, common to a class of systems. So for example, an example where it is insensitive to the system is in so-called unimodal maps. So Feigenbaum studied it in the logistic map, where you have Rx times 1 minus x. So it is, but as long as the map has that gross shape, it need not be a quadratic function, it may be some trigonometric function or even some piecewise linear function. As long as it is unimodal with one maximum, the Feigenbaum constants are the same. So there is a universality in that class of maps. But one cannot expect the same Feigenbaum constant or the same scaling constant to also appear in this Hamiltonian system. They have different exponents. So, but it is still, I don't think there is a clear answer to this yet, but one would like to know whether one can talk about a class of Hamiltonian systems which have sort of common exponents or common power law behaviors. Or, for instance, even, I mean, there are yet other phenomena here. I talked about this cascade of bifurcations. Is that again something that one sees in more than one system? I gave a couple of examples. You mentioned the anharmonic oscillator. Yoshida has studied that, and there too there's a cascade of bifurcations. So there is something common to several of these systems, but the connection to chaos is still not very clear, even in our system. So it is not clear how this bifurcation cascade is linked to the development of chaos, if at all. So I think these are open questions. Yeah, but I think first one needs to find common phenomena, and that is certainly going on. And Feigenbaum has carried this very far in the case of the logistic map or unimodal maps. He has developed a renormalization group method to calculate the Feigenbaum constant through some fixed point of a renormalization group map, and the eigenvalues of that linearization gives you the Feigenbaum constant. So such a theory is not available for continuous time dynamical systems as far as I know yet. So that is something one would like to do.
Yeah, it's a slightly pedagogical kind of question. So you said about the pendulas and breathers, right? So, but qualitatively, even breathers looks like a pendula, kind of a complicated pendula. So breathers are usually found in various kind of systems. So can you quite distinguish these two qualitatively? Yeah.
Okay. All right. So, I mean, in this system, they're clearly distinguishable in the sense that in a pendulum, two rotors form a molecule and the third one oscillates about them. Whereas in a isosceles breather, two are, it's got one at the center and two going apart. Yeah. So they're quite different in that sense. The solution are also quite different. One of the reasons we are calling it a breather is that it looks like a breathing system. Yeah, the front and back of and something in the middle. There may even be some connection to the breathers in soliton systems. You might have even in Sine Gordon and other such systems, you have breather solutions. We have not investigated this connection carefully, but the Sine Gordon system does arrive as an infinite rotor limit of our system. It's possible that some of the solutions we have got in that limit go over to those breathers. But there seems to be quite some difference between these two classes of solutions. The breathers do not display this accumulating sequence of stability transitions. It's just not there. They have just one stability transition at some critical energy. They don't have this intricate dynamics, whereas the pendula have this very intricate dynamics. So they seem to be somewhat qualitatively different and dynamically also different solutions. I can further elaborate in the sense that the pendula lie on what is called a homoclinic orbit from a saddle point back to itself, whereas the isosceles breather lie on a heteroclinic orbit between a saddle point and a maximum of the potential. So there are many features that are somewhat different. Yeah, but what it ties them together is that they are both two-body solutions exported to three-body problems. So in that way, they are similar.
So you basically showed how you can map the problem of chaos in Newtonian mechanics to a problem of Riemannian geometry, right? So do people do the reverse? People who are working in gravity, they may study chaos in Riemannian geometry. So they reverse the map and use the techniques of classical mechanics?
Sure. Okay. So there's one difference here. The kind of geometry I described is Riemannian, not Lorentzian. So this is the signature of the metric is all positive, whereas in in the application to relativity, it is So there is that slight difference that the metrics that one gets in this geometrization of mechanics is not Lorentzian. But putting that aside, yours is a good question. One can look at certain systems of geodesics and interpret them mechanically. And this was done more than 100 years ago, starting with Hadamard. So what they look at is your manifold is a two-dimensional surface. So the simplest two-dimensional surface is a sphere, but it has positive curvature. The next one is a torus. A torus, suitably interpreted, is flat, yeah, or it has some positive and negative curvature with embedded in 3 dimensions. But the standard torus is flat. And then you have the higher tori or higher handle bodies, a torus with an extra handle. It turns out that those manifolds, higher genus surfaces, can admit constant negative curvature Riemannian metrics. Okay. So you got genus 2, 3, 4, and so on. So one can study geodesic motion on these higher dimensional tori, like a pretzel or others, tengorel, or there are, you can, jalebi or whatever you want. And it turns out that that geodesic dynamics is very interesting and has been studied in depth by Sinai, the Russian school. And they find that the geodesic, so you interpret those geodesics as the trajectories of some mechanical system. What is the kinetic energy of that mechanical system? It is basically the integral of the square of the length. Yeah, it's the action that leads to geodesics as the trajectories. So they have shown that geodesic dynamics on constant negative curvature Riemann surfaces is ergodic. They have actually proved this. And so that gives a sort of a standard example of chaos in a mechanical system that is inspired by this geometry and geodesics of a metric. So definitely you can go the other way around. And it is very insightful. And there are very deep results on this, even in the quantum theory, where this goes to Selberg, goes back to Selberg, where he has connected the geodesics and their motion on these constant negative curvature surfaces to the spectrum of the Laplace operator. This is the Hamiltonian, the quantum theory. There's a deep relation between these two, given by so-called trace formula, Selberg trace formula. Interestingly, it was published in an Indian journal. This is more than 50, 60 years ago. And that was generalized by Gutzwiller to an approximate formula connecting classical and quantum mechanics. It's called Gutzwiller trace formula. So, but anyway, to answer your question, you can go backwards. You can take geodesic dynamics and view it as a mechanical system. I mean, that leaves aside the question of chaos in gravitational physics. Yeah, you can have bodies, even relativistic systems that are chaotic.
More questions? He'll be available in the afternoon for some time if any of the students want to interact. So let me thank you for a wonderful lecture. I take this opportunity also to welcome Mrs. Leela teacher to hand over a small token of appreciation from their family part.
Thank you. Thank you so much. Yes, I am very glad to. Yeah, sure. I'm so happy to meet you. I have met your husband at Mudibidri in Karnataka. I don't know if you remember, but it was 2016 February or so. So, thank you so much. I'm glad you could come.
Thank you.
And it's great that you have instituted this lecture in his memory. To all those who contributed to instituting it and perpetuating it, my congratulations, and I hope it continues.
So with that, we come to the end of the session. So let me thank Professor for the wonderful exposition to the age-old problem, and starting from way back to the modern era of one of the classic problems in physics. So let me thank him and all those who have joined, especially family of Professor M.C. Valsakumar. And I also thank Shan especially for organizing all the online teaching and so on. So I hope, so it's lunchtime, so one word thank you for all. So we'll meet you again sometime. See you.